Hello, I'm Mansi Limbu. I'll be presenting our paper Heterogeneous Team Coordination on Partially Observable Graphs with Realistic Communication. This problem is a general form of the TCGRE problem that introduces risks and support elements, example fire and fire extinguisher in robot path planning. The paper formulates TCGRE is a constant optimization challenge where robots either follow the naive or path independently or collaborate with the teammates to travel risky edges and minimize the overall cost to reach their goal. However, the original TCGRE has three strong assumptions. All robots are homogeneous, know the global graph, and can communicate with each other and the central controller. We relax these assumptions by allowing robots with different strengths, leading to different edge costs, relying on sensor-based partial observations in unknown environment and coordinating via close-range communication to share partial maps. For example, a red car and a blue drone sense nearby regions, forming partial maps. When close enough, they exchange maps, creating a combined map like the purple area. We extend TCGRE with three more constraints. Equation 5, 6, 7 for partial map updates, exchange, and communication-based coordination. The objective function also differs as its costs now depend on the robot types. We divide the problem into two. Within the partial map, subproblem 1 becomes a single agent shortest path problem, while subproblem 2 is TCGRE for a group with varying edge costs. The robot lacking a full map moves towards a subgoal within its partial map. As the partial map expands, the subgoal updates until the goal is detected. We assign the subgoal using a greedy method, considering the shortest path and estimated distance to final goal. For a robot group sharing a partial map, we assign subgoal combinations using a heuristic approach. This forms a multiple choice knapsack problem, and we currently use exhaustive search as the partial map and the number of robots are typically small. Robots may switch between individual movement and coordination. The previous method treats this mode separately, causing performance loss. To improve, we pair robots with closest goals, aligning their subgoals for better coordination. Each robot is assigned a scheme and the heuristic includes the Euclidean distance between their subgoals. The algorithm runs algo 1 for solo robots and algo 2 for robot groups at each time step, repeating until all reach their goals. We conducted an ablation study where we compare algo 3 against 3 baseline, algo 3 without C3 or base team at cost, algo 3 with epsilon greedy, and a naive individual movement approach. Result shows algo 3 performs similarly to the epsilon greedy model, sometimes better or worse, while the naive approach consistently underperforms. The algo 3 without C3 occasionally performs well but can perform worse than the naive approach due to independent subproblem treatment and non-optimality from using Roca star on larger graphs. In the future, we plan to add communication cost data filtering for limited bandwidth, predict robot location in unknown graphs, and investigate the graph structure influence for more comprehensive solution.